Hi everybody, my name is Andrew McIntosh and I'm the head of the School of Earth, Atmosphere and Environment at Monash University. Today I'm excited to be talking with you about Antarctica, a place I'm passionate about and that I've had the privilege of visiting many times. Antarctica is the coldest, driest and most remote continent on Earth. It's probably best known to you for its penguins, but today I'm going to be talking about the ice sheet, which covers an area larger than Australia and is more than 4 kilometres thick at its centre. If all of this ice was to melt, it would fundamentally transform our planet's coastlines, flooding cities and in some cases whole countries. So the question is, what do we need to do to better predict the future of Antarctica and its ice sheet? Today I'm going to be talking about the exciting work we're going to be doing at Monash. Monash University is now the global centre of an Antarctic research hub, and over the next 7 years there'll be opportunity for many of you to get involved. So today we're going to be talking about the exciting science that will lead to a better understanding of Antarctica and therefore our planet's environmental future. Let's have a look at how Antarctica is changing today. I'm going to show you a movie of the Antarctic ice sheet that's based on data from 2 NASA satellites that detect changes in the Earth's gravity as the ice grows or shrinks. Around 20 years ago, when I started out as a scientist, we thought Antarctica wasn't changing very much. We thought there was an approximate balance between the snowfall that was coming in and the ice loss at the margins. But as the 2000s progressed, things really started to heat up. What we're focusing on here is the change over a number of years. The map to the right shows the cumulative mass pattern. Reds are for areas of ice loss and blue for areas of ice gain over the entire Antarctic ice sheet. As time goes on, and in particular after 2007, a huge red spot develops over West Antarctica. We also see areas of mass gain due to increased snowfall, but they're not nearly enough to offset the loss. It's this creeping, growing, giant red spot, which is due to the rapid acceleration of ice, thinning of the ice sheet, and retreat of its major outlet glaciers. And all of this has been driven by warming of the ocean. The Intergovernmental Panel for Climate Change, of which I'm an author, has indicated that mass loss in West Antarctica could be the start of an unstoppable and irreversible feedback. This could result in the entire loss of the West Antarctic ice sheet in coming centuries. Parts of the East Antarctic ice sheet directly to the south of us here in Australia are also potentially vulnerable. And if the West and East Antarctic ice sheets together start to disintegrate, then we could get metres of sea level rise over coming centuries. To learn if this is really going to be the case, we need to do a few critical things. The first thing we need are longer observations of the ice sheet. Current observations from satellites only go back a few decades, and this is not nearly long enough to know whether the current behaviour is unusual. The second thing we need are better observations of the bedrock beneath Antarctica and of the oceans surrounding it. The oceans have been warming, but is that the same everywhere? How does that affect the ice sheet? We don't really understand it yet. The last thing we need, and this is really critical, are more accurate computer models of the ice sheet. Computer models are amazing. They allow us to imagine the future and calculate the sea level contribution from Antarctica. These models need to take into consideration our greenhouse gas choices, because ultimately it's going to be our decision as humans that makes the difference about how the Antarctic ice sheet changes. I'm now going to pass over to my awesome colleagues who will talk about each one of these topics in turn.
The geological past provides valuable insight into how the Antarctic ice sheet is changing today and how it will change into the future. Rocks and sediments record past times when the ice sheet grew and retreated, allowing us to better understand how ice sheets respond to changes in the climate. We are particularly interested in when, where and how the Antarctic ice sheet retreated after the last ice age. And to answer these questions takes us to Antarctica. We fly south to the great white continent of Antarctica. We set up camp, consisting of polar tents and an igloo toilet in the mountains alongside fast-flowing outlets of the ice sheet. Our aim is to collect rock samples, ice-free bedrock surfaces and perched cobbles, often using power tools, hammer and chisels. Each sample can tell us when the ice sheet surface lowered to expose that rock surface. By collecting rocks at multiple elevations above the modern ice surface, we can produce a timeline of past ice sheet thinning. We then return with our rock samples, which we then process in the lab.
I'm a field and lab-based scientist, and I love both for very different reasons. It's really rewarding to see a sample through the whole process of turning a rock into an age. This type of science is really interesting because it's a combination of geology, geography, and chemistry. Cosmic rays produce elements that can be used to date the exposure age of a rock. In order to count the number of atoms found in a rock, we have to physically and chemically process it. To physically process the rock, we cut it into manageable sizes and then crush it into a fine powder and separate out the mineral quartz. We take the quartz powder and we clean it with a few different types of acid to remove any impurities. Once the quartz is pure, the sample is digested in acid. The remaining material is then separated by element, dried and packed into a target, and finally sent for analysis. The elemental concentration of the sample is then used to calculate the exposure age for the sample. All of the work that it takes to do this type of analysis can be done on campus.
By looking into the geological past, we found that the rates of rapid ice sheet thinning that you see in parts of Antarctica today could persist for centuries. This has important implications for the amount of potential ice loss and corresponding sea level rise into the future.
Modern observations tell us about the current state of Antarctica, including how it's contributing to sea level rise. And they can also tell us about the processes that are driving change. We know that the ocean is the biggest driver of current ice melting and loss from Antarctica. Ocean melting is therefore one of the most crucial measurements we collect when we go to the field. As the ocean melts beneath the floating ice shelves that encircle Antarctica, the ice that's grounded on bedrock upstream can actually speed up and flow faster into the oceans. These days we have satellite records, such as NASA's MEASURES dataset, that can show us how fast the ice is flowing. From these data, you can really see that the patterns of ice flow in Antarctica look a lot like water flow on land, from small streams into large tributaries that flow into the ocean. These patterns of ice flow are strongly guided by the bed topography below, which is another very important quantity to measure. But how do we measure ocean melting and bed topography? As part of my fieldwork with the IceCap project, which is a collaboration between Australia, the UK, the US and France, I've been to regions in East Antarctica that are rapidly losing mass. We fly a small Basler aircraft that has radar antenna on each wing. These radar are ice-penetrating radar, so they can actually return us information about the bed topography beneath the ice, so that we can understand how the ice is flowing. We also measure ocean salinity, temperature and bathymetry using airborne probes that we launch from the aircraft. These data tell us about the types of water currents that are making it under the ice shelf to melt the ice. With this information of bed topography and ocean melting, we can understand how the Antarctic ice sheet is currently changing. With further modern observations, we can construct models, which we then use to better predict how Antarctica might change in the future, including how sensitive it is to climate change. So what do we mean by models of Antarctica? Well, models are tools that we use to understand the environment, the processes that are operating, and how they might change in the future. The ice sheet models that we use are made up of mathematical formula that we translate into computer code and that integrate real-world data, such as ice speed and thickness, to build up a picture of the current state of Antarctica and how it might change over time. But why do we need models? Well, there are two key reasons. Firstly, we need models to investigate the processes behind ice sheet flow and its interactions with the ocean, atmosphere, and solid earth. For example, I talked earlier about ocean melting beneath ice shelves, but the interactions between the oceans and the ice are highly complex, and they vary from one ice shelf to another depending on the ocean currents, the bathymetry, and many other factors. Models can help us to understand these processes and how they might change depending on the local environmental conditions. Secondly, we need models to predict how Antarctica might change in the future or how it's changed in the past. For example, we know that Antarctic ice loss has a huge impact on sea level rise. If West Antarctica were to collapse, we might see 3 meters of global sea level rise. But when will this happen? And what ocean and atmospheric conditions would cause this to happen? Will all of West Antarctica collapse or only some parts of it? We really need to be able to answer these questions for governments and policymakers that are planning for climate change, and models really are our best tools for answering these.
Many people ask me, how do I become an Antarctic scientist? How do I become a glaciologist? The answer is that there are many different pathways, but you can follow them all in our school. If you're a geographer, great. A geologist, fantastic. A meteorologist, a mathematician, or a physicist, come and join our ice sheet modelling team. What about geochemistry? Well, we're building a new lab for you right now. So no matter what your background or pathway, there's a way that you can get into Antarctic science if you're passionate about it, and I'd love to support you and see you in our school.